cell potentials. Now we're going to hone in on a certain type of cell potential, the reduction standard cell potential. Let's have a look. Before we look at any of these, the reduction standard guideline chart, in order to solve our practice problems later on in this video, we have to understand what a cell potential is. Now in this video, we're going to cover how cell potentials revolve around the terminology of potential difference. Now, this should be quite familiar to you, especially in your junior grades. You should understand that potential difference is abbreviated as V. Now, V is also known as voltage. So really, they're the same thing, okay? Voltage and potential difference, they're honestly synonymous. Now, what was voltage? Well, in your, again, previous grades, you would have maybe learned about it as the difference in current coming in and the current leaving. So it's pretty much the amount of current that got used up. So for example, let's say we have this individual here, okay, and they're going towards the gym, and then let's say this is a door, okay, so this is, you know, the gym, okay, to enter towards the gym. This person has a lot of energy before going through that door, okay, before going to the gym. So once that person goes into the gym, okay, and then leaves the gym, so right now this person has a lot of energy, okay, and then when this person leaves the gym, that same person, now they have lost all that energy, okay, because they've used up their amount of calories in the gym to work out. So that's maybe how you've learned it. It's actually a little bit more complex than that. Let's have a look at an in-depth analysis. If we look at one charge over here and another charge over here, so let's say it's highly negative in this end and highly positive in this end, okay, and we have some electrons here definitely wanting to go towards the positive end, right? So again, there is no movement of energy, okay, there is no kinetic energy right now. However, there is energy that is existing, okay? Energy can still exist. There is a foundation for it, even if it's not even moving, okay? So obviously this is called potential energy. It has the potential to go from here and then wanting to jump over there, okay? So we can write here that potential energy exists. So PE, okay, so PE stands for the potential energy. So PE exists when there are two charges separated. So there's some sort of force acting on this end over here, and that force is trying to bring obviously this one together with that end over there, okay? And when that gets released, okay, this amount of energy, the flow of electrons, finally able to jump from here to here. That is known as the voltage. So to actually summarize that on the side, it's actually the amount of energy a unit of charge would gain by moving from one point to another. Now, it's not that clear cut because all of this, right, the amount of energy flowing from here to here, it all depends on the type of oxidizing agent. It depends on the type of reducing agent, and it actually depends as well on the concentration of salt solutions as well, and the temperature of these particular solutions, and the atmospheric temperature and pressure. In the previous video, we actually looked at this Danielle cell. Please have a look at the video link in the description that revolves around this cell over here. It's a prerequisite to this video. We looked at this Danielle cell and we identified which end, this side or this side, would be the anode or the cathode, okay? Because we have to determine which one oxidizes and which one gets reduced, okay? And like I said, it depends on the concentration of the salt solution, okay? So what salt bridge solution that do we have here to help replenish the amount of charges that are in this aqueous solution and the amount of charges in this aqueous solution to make sure that we have net neutrality. We don't want a buildup of excess charges in either one, right? So it matters about the concentration and the type of aqueous solution that we have right over here in our salt bridge. And of course, it depends on the temperature of these solutions and the atmospheric temperature and pressure. Okay, so what particular pressure are we going to be referencing? So we need a constant condition to arbitrarily reference to. Alright, so this stands for arbitrarily, to arbitrarily reference. There are these 5 conditions. Okay, we'll look at the first one here. We're always going to be dealing with the salt solutions as a concentration of 1 molarity or 1 mole per liter. Okay, for the concentration of the salt solutions. Our second point is that it needs to be at 1 atm. Okay, also known as about 101.3 kilopascals or kPa. Okay, the electrodes, so this one right over there and this one right over there. Okay, again, this one could be the one that is being minimized and being lost, and maybe this one over here is being gained and getting bigger, or maybe this one here is getting oxidized and is being lost, and this one here, the cathode, is getting bigger. Okay, you have to identify and indicate it. Regardless, the electrodes must be, okay, so these electrodes must be pure metals. Okay, they can't be non-metals or metalloids. Okay, they're going to be pure metals. Okay, and the temperature must be at 25 degrees Celsius. And the very last point, no electricity flows in the cell. Okay, so it has to be blanket. We call all of this, right, the constant conditions that we arbitrarily reference to, we call all of this the standard cell potential. We typically like to use hydrogen. Okay, why do we like to use hydrogen? Well, let's say we have hydrogen over here. Again, it is a diatomic molecule, right? Hofbrinkel, right? Or have no fear by school beer, right? Hydrogen is one of those. So it has to be paired up by itself. And if we have hydrogen on the other side as well, what is going to happen? Well, if this here is the atom, this here might be the ion. So let's put a 1 plus over there. Now, the law of conservation of mass states that this side and this side must be the same, okay, in terms of the number of atoms. So if there's 2 over here, we're going to be putting 2 over there, so let's put a 2 over there. Now, obviously, there is no net neutrality. This is a 2 plus, okay, a plus 2. So we got to be putting a negative 2, so we're just going to be 2, we're going to be putting 2 electrons over there to balance it out. So this half reaction can be oxidized, can be an oxy or reducing agent. If that's the case, its voltage is actually going to be 0. Now, how do we know that this hydrogen can be an oxidizing or reducing agent? I want you to think about this again back in your previous grades when you look at the Bohr diagram, okay, for the ion. If we have hydrogen, okay, let's say this is hydrogen, and hydrogen is obviously 1 proton because its atomic number is obviously 1. What would its neutron number be? Hopefully you can kind of remember this. If you don't remember, you have to know that the neutron number, okay, is equal to the mass number minus the atomic number. So the mass number is obviously, I think, 1.01, something like that. Okay, AMU are atomic mass units, subtracted by the atomic number, which is obviously just 1, so you pretty much can just round down to 0. Okay, so there will be 0 neutrons. This is why hydrogens can be known as the protons. Remember how we talked about in acids and bases, right? The acids were the donation of the protons, whereas the bases would be the acceptance of the protons, and we'll use H as an arbitrary proton. If you need more review on that, please see the video link in the description where we talk about this. And now we're obviously missing the electron. Okay, so we have the proton, we have the neutron. Where is the electron? Okay, so we're going to be drawing, because this here is a nucleus, right? So after that, we're going to be drawing our first ring, and that's going to be where our electron will be residing. Okay, you can't really see it there. I'm just going to make it green. Now you should have learned that there are 2 ways that we can represent it, okay? Obviously, the first method that might be more familiar to you is that the first ring must always have a maximum of 2 electrons in order to be stable. So right now we only have 1. In order to make that second one, we got to be bringing another electron over there, okay? So there could be a gain of electron, okay? Or what could happen is this one here can be removed, okay? Because then we're still becoming stable as well, okay? We're not necessarily having 2 in that first ring, like how you were previously taught from your teacher, but technically it is an answer as well. You could get rid of this electron here so that there are no more electrons on that first ring. It can still be stable that way, okay? So if we kind of get rid of that, then we have a loss of an electron. So in terms of the number of valence electrons, okay, if you gained 1 electron, then you'll have a valence electron of 2. Whereas if you lost 1 electron, like what we did over there, it's completely gone. Obviously, there are no electrons on that very last ring. In this case, we only have 1 ring, okay? So it's still technically the last ring. The valence electron would then be 0. So in terms of its charge, if it gained 1 electron, what would its charge be? It had 1 proton, okay, which is positively charged before, and it had 1 electron, which is negatively charged. If you gain 1 more electron, you now have 2 electrons. Okay, so now you have just 1 minus 2, which would be giving you a charge of -1. Whereas if we take the second scenario and you lost that electron, like as you can see over there, again, we started off with 1 proton. Okay, we had 1 electron, but we just lost that, right? So now we have 0 electrons. So what would its charge be? It would be a +1 charge. This is why we use this hydrogen as a standard cell potential arbitrary reference reaction, the half reaction that we want to always refer to, okay? Because it can be oxidized or it can be reduced. Of course, you should already know this from the previous video, but I just want to quickly recap in case you forgot. If it is an oxidizing agent, it is a reduction half cell. If it is a reducing agent, it is going to be an oxidizing half cell. Now there is one particular formula that I need you to remember. Your E naught cell is going to always equal your E naught cathode minus your E naught anode. Another way you could say this is standard. Okay, so E standard of the cell is equal to the E standard of the cathode minus the E standard of the anode. It's important to understand that this E standard of the cathode is the reduction potential for the cathode. Okay, so it's the reduction potential for the cathode. Whereas the E standard of the anode, okay, is the reduction potential as well, but it's going to be for the anode half reaction. You can find the standards, okay, the standard reduction potentials, okay, for the cathode and the anode in the reference chart that I'm going to be showing you shortly. Once you find those and you find the difference between them, if this V ends up becoming positive, okay, because obviously we're finding the potential difference, okay, between the cathode and the anode, which is known as the voltage. So once you find that difference, we have found voltage. So if that voltage value number that you get becomes positive, it is spontaneous. Okay, so it'll proceed in the way that is written. Okay, whereas if the voltage ends up becoming negative, it is not gonna proceed spontaneously. So this is the chart that I promised you. Okay, we even looked at this in the previous video as well, in the Danielle cell video. As you can see, this E standard, okay, also known as voltage, represented there. Okay, you can see that there as well. Now just a disclaimer that these have a few half reactions, okay, these ones over here and these ones over here, but the next three practice problems that I'm going to be doing with you together, I don't have these particular half reactions. Okay, obviously the chart is much bigger. Okay, your teacher or professor is going to be giving you that anyway. You obviously don't have to be memorizing it, but if there are any practice problems that we're going to be running into that does not have the particular half reaction that we need, okay, I'm just gonna show it to you on the side. Just know that there is a bigger chart than this when you solve these on your own. Okay, the last two green questions of the day that you're going to be doing on your own, I give you the answer key to, they will be outlined within these charts, so don't worry about that. Write the oxidation and reduction half reactions. So first of all, we're going to obviously look at the first diatomic molecule that we see over here. It is a Cl2, so let's write it out. And what does it produce as its counterpart ion? Okay, that's an ion, obviously the 2Cl minus. So I've written that there as such. You can keep the states if you want. Obviously this is not balanced in terms of its charges. This is a -2 on the right side, this is a 0 on the left side, so you should be adding 2 electrons. Okay, so we've done that. Now we're going to do the same thing for the Brs, okay, our bromine. So we have 2 Br minus becoming our Br2s. 2 minus over here, 0 over here, so let's add 2 electrons. Which one is being oxidized and which one is being reduced? Obviously this one here has obtained or received electrons, right, because it's on the reactant side. So of course this one here has received the electrons, so this one here would be the reduction. Okay, it's not losing electrons. Okay, obviously this one here is losing electrons, right? This arrow symbol means yield or produced, right? So it is literally producing what? It is producing electrons. Okay, so obviously electrons are being lost here in this case. Okay, so if they're being lost here, they are being retrieved or gained over here. Okay, so this one over here would be your reduction. This one over here would be your oxidation. Next, determine the standard cell potentials for galvanic cells in which these reactions occur. Okay, so I know we already decided that this one here was the reduction, okay? So remember, for the ones that are being reduced, they are on the cathode end, okay? Whereas the ones that are being oxidized are the anode end. We could write over here that the cathode, the E cathode, is equal to a particular value. Again, we don't have it here in this chart. And the E anode, the E standard anode, is going to be another particular number. Again, it's not in this chart either, okay? On a bigger chart, okay, again, that you will be given from your teacher or professor, should be 1.36, okay? Should be 1.36 for the Cl2 plus 2 electrons yielding the 2 Cl minus, okay? 1.36. So that should be somewhere like, I don't know, somewhere around here, okay, within the chart, within the bigger chart that you're going to be getting. Whereas the E standard anode would be 1.07. Oh, never mind. It actually is over here, okay, for your Br2. So that's nice, all right? So we have the Br2 ones, but we just don't have the Cl2s. Like I don't see any chlorines over here. So we know that the formula was just the cathode minus the anode. It gives you a 0.29 voltage or electric potential difference, okay? So how do we make a statement about this? Is it spontaneous or is it not going to be spontaneous? Well, it's obviously positive, so it's going to be spontaneous. So let's write this out. We have our MgS. That's going to stay the way it is. And as you can see, we can tell that there are going to be spectator ions here and spectator ions over here. So let's get rid of any spectators that we see. So we have 2 Ag plus AQ followed by 2 of these nitrates. Yielding, we have 1 Mg. It obviously has an 2 plus charge because it is a group 2 element. And we have 2 NO3s. And we know NO3 always has a charge of -1, polyatomic ion, followed by our 2 AgS. So let's cancel out the spectators. Obviously this one here are the same. So let's continue downwards and bring down what we have left over. How do we finish this off? Well, we got to determine the oxidation and reductions, okay? So let's get our MgS. Where is its counterpart? Mg2 plus is its cation. This is a +2, so we got to balance it out. So we got to be putting a -2 over here. Now we are good. And then we got to do our 2 Ag plus. For our counterpart 2 Ag. There's +2 over here. Let's put a 2 minus over there now that we are balanced neutrality. Now we got to determine which one is oxidized. Obviously this one here is being oxidized. Okay, it is losing the electrons. So this one here is oxidation. This one here, it has received on the reactant end. Okay, so this is obviously the gaining end, also known as the reduced end. Okay, so oxidization, okay, this would be the anode, and the reduction would be the cathode. So let's determine the standard cell potentials. So our E cathode, okay, is going to be this one here, 2 Ag plus 2 electrons yielding the 2 AgS. Again, it's not given in that chart, but I'll just tell you what the value is. It is 0.80 volts, okay? And then the E anode, again, not in the chart that I provided you in the beginning, but the anode value is going to be -2.37. So these are all in volts. So we know the formula, this one minus this one, right? So we got our 0.80 minus our 2.37. What do you end up getting? Getting a value of 3.17. And this is obviously going to be all in volts You could be putting volts here as well, volts, volts, and obviously this one here means that it is spontaneous. I want you to try this one on your own. Okay, I'm gonna do this one with you as well, but just pause the video, try it yourself, and then I'll do a play-by-play with you shortly. Hopefully you tried it on your own. Let's do it together. So you have your tin here, and it is yielding your SnBr2. Okay, actually, you know what, let's break these up, okay, for the net ionic equations. So we have our SNS with, again, 2 hydrogens over here. We know hydrogens have a +1 charge, and 2 Brs. We know it has a negative charge, and we have just 1 Sn. Okay, we know Sn, as you can see over here, it has a 2+ charge because it's written as a subscript down here. We have 2 Brs, and again, has a charge of -1, obviously. Group 17 element, and then we have H2 gas. Okay, so let's cancel out our spectators, this one and this one over here. So what do we have left? We have our SNS plus our 2 hydrogens, producing our SN2 plus and our H2. What do we do now in this case? Well, we have to see our Sn and its counterpart SN2 plus. Again, 2 plus here, let's add 2 electrons here to balance it out, and then now we have our next one, our 2H plus, to our H2 atom, 2 pluses here, let's add 2 electrons here for neutrality, and we are done. Okay, so which one is being oxidized? Obviously this one here. And which one is being reduced? Obviously this one here. So this here is the anode, this here is the cathode. You should have already remembered that our hydrogens, okay, was our arbitrary reference, okay, of a potential difference of 0, right? In this case, it's acting as the cathode. So we can just put a simple 0, okay, whereas this one over here, not in the chart that I gave you, but just letting you know the value is -0.14 volts. Okay, so obviously this one subtracts with this one. This gives you a 0.14 volt. Obviously this here, again, spontaneous. So it seems like all 3 ended up becoming spontaneous. So this is the green question of the day. This here is going to be the first one. This here is going to be the second one. Please pause the video, try these on your own, and I'll be giving you the answer shortly. I'll also pull up the 2 charts, okay? It should have all of the ample amount of standard potentials for you. So use this chart as well as this chart over here. This is the answer to the first question. This is the answer to the second question.